All right, team, I always save the best for last for this journey we're on for gases. We've been avoiding this the entire time. I hinted at it in the very first video because I like to start with kinetic molecular theory. And if you remember from kinetic molecular theory, a couple of those postulates, we made some pretty hefty assumptions here to simplify the mathematics so we could use the ideal gas equation, P equals nRT. Remember the two assumptions? We assume that the particle volume, the actual volume of the gas particles themselves, those tiny little dots, are so tiny. How tiny are they? They're so tiny relative to the container, they're effectively zero. Right? So the volume of the gas sample is the volume of the container. We made that assumption. It's not technically true. The gas particles actually take up some volume. Okay, so maybe that assumption. Is it a valid assumption? We'll find out about that in a second. We also assume that the interactive forces between particles, and find out those are intermolecular forces, are zero, right? So if I've got two particles moving and they do a flyby, they don't even notice each other. Only when there's a direct contact do we account for any kinetic energy transfer. But other than that, we're assuming no interact. They're not aware of each other unless they bonk into each other. So we're assuming those forces are zero. In real life, not so true. You can have some gases that are polar, some are non-polar, right? So you might have two polar gases that are going like this, and all of a sudden, or one's heading over to the wall, and the other ones start pulling it back, saying, "No, come back to us." It's gonna create some issues on the pressure. Right? But if we make those assumptions, we get what's called an ideal gas. We're going to find out that's pretty valid at normal laboratory conditions of, roughly atmospheric pressure and room temperature. It's pretty valid. And we'll look at the validity of that statement. But if we do account for those two gases, we get what's called those two gases. If we account for those two factors, if we actually account for the gas particle volume and make a correction to the overall volumes by taking the overall volume of the container and subtracting out the gas particle volume, that's a little more accurate. And if we make an adjustment to the pressure and account for the intermolecular forces between the gas particles, which can change what we would think is what would be the pressure, we get what's called a real gas. And Johannes van der Waals looked at this. Let's take a look at what van der Waals did. All right, let's take factor number one, the gas particle volume. Then we'll do the same thing on the next board, accounting for the interactive forces between the particles. So let's take a look, and hopefully you can appreciate qualitatively why this becomes important. So let's say we got a container with, I just have 10 gas particles in there. Doesn't matter what the gas is. So we got a higher volume here, and let's compare the same 10 particles to a lower volume container, right? So we got this big volume container. You got more room for the particles to move around, so they're not banging into each other as much, blah, blah, blah. Whereas if we have the lower volume, now they're kind of compacted in there. They're hitting each other more often, right? So remember, this is a higher pressure. Remember Boyle's law, right? So the larger the volume, the lower the pressure, the higher the volume, the lower the volume, the higher the pressure, because there's more collisions, more collision frequency. So would you agree, normally we would assume the gas particle volume is irrelevant compared to the size of the container. And the bigger the size of the container, the more irrelevant the gas particle volume is. But as you make that gas chamber smaller and smaller and smaller and smaller, the gas particles get smushed closer and closer together, and they become a more significant percentage of the overall container volume. See what I'm saying? So the lower the volume or the higher pressure your sample is, the more error that occurs, assuming the gas particles are actually have a volume of zero. Right? So it becomes more important to account for the effect of real gases and the gas particle volume as the lower volume or higher pressure. We good? Can you see that? Right? So what van der Waals did, and I'll write this up when I show you his equation. What van der Waals did is he accounted for this gas particle volume, but including this constant b, little b. I've heard people call that the excluded volume per mole of gas. Right? And it's just a constant. It has units of liters per mole, excluded volume per mole. And it's a constant for each gas, so every gas has a different value. All right? And you can look these up in the Handbook of Chemistry and Physics and other sources and whatnot. It's specific to the identity of gas, and you'll see as the size of the gas gets bigger, B gets bigger. Makes sense, right? Even though technically we don't worry about that for ideal gases, but really if the gas is bigger, if each particle's bigger, it's going to encompass a little bit more volume, statistically speaking. We good? So if that's the volume per mole, if we take the moles, N, times the excluded volume per mole, B, so that factor NB should be the volume of the gas particles. So if we want to make a correction from the ideal gas equation, remember PV equals nRT. Well, let's take that V term now and subtract the actual gas particle volume. Because we normally just use the container volume, right? Well, it's technically not correct. So let's take the container volume and subtract the volume of the gas particles, NB. That will be the volume actually available for a gas particle motion. Sweet. So in the gas equation for real gases, instead of using V, we're going to use V minus NB, correcting for that. Hey, let's look at the pressure correction. All right, for the second assumption we made in kinetic molecular theory, or KMT, was that the intermolecular forces or attractive or repulsive forces between particles was non-existent. Well, actually, depending on polarity, and we haven't talked about polarity yet, but some gas molecules may be more attracted to each other than others. That's a term called polarity. We're going to learn one of our later chapters. If we do account for that the van der Waals did, for example, let's say we got a chamber with these three particles, and this one is heading over to the wall to go boom, apply an impulse, collision frequency times impulse is pressure. That creates pressure. But for an ideal gas, we're assuming that these two particles have no impact on that one at all, right? No attractive forces at all. So they're just moving around independently. But if we account for the real gas, and that one again is heading to the wall to strike and create pressure, but if we allow the fact that there's attractive forces, these two will actually pull this one back away from the wall a little bit. So it won't hit with much impulse as it would have. So it creates less pressure than you think. So if you account for real gases, or real gas behavior, the pressure is actually less than what we would get if we assumed ideal gas behavior. So we're going to have to mathematically account for that if we want to deal with real gases. Right? How do we mathematically account for these attractive forces between these particles, pulling them away, right? This guy's trying to hit the wall, the other two going, no, we like you, come back to us, right? They can't stop him from hitting it, but he's not going to hit it quite as hard. So again, the impulse will be less. So what we do is we incorporate another constant, like we use that constant B to account for the gas particle volume. Well, we use the constant A, so I guess I should have done this one first, A before B, whatever. A is I don't know the name of that one off the top of my head. Right? The B was the excluded volume per mole. So A is a constant specific to each gas, so it's going to be different for each gas. You can look them up in the Handbook of Chemistry and Physics. That accounts for those intermolecular forces. And obviously, the stronger those molecules or atoms are attracted to each other, the larger the value of A is going to be. And to incorporate that into a pressure correction term, you get this overall correction factor that you're going to see, N squared A over V squared. You're going to see that next to the pressure term. So instead of PV equals nRT, you're going to get P corrected, V corrected equals nRT. Let's do it on the next page, next board. All right, here we go. We finally arrived. Johannes van der Waals, 1873. A lot of cool stuff in the 1800s. Adjusted the ideal gas equation, PV equals nRT, to account for these two factors, gas particle volume and the intermolecular forces of attraction between the gas particles. So we get what we call the real gas equation. Some people call it the van der Waals equation. So we get the pressure term with that correction factor, so P plus N squared A over V squared. And then the volume term with the volume correction, V minus NB, remember that NB correction, equals nRT. Now, if we assume ideal gas behavior, if A equals 0 and B equals 0, remember, assuming ideal gas behavior, you're assuming the gas particle volume is 0, so B would be 0. You're assuming there's no interactive forces, so A would be 0. We get an ideal gas, right? That's technically what we're doing. We're assuming A and B are 0 for an ideal gas. And that simplifies the math. Well, what happens when A is 0? This whole correction term goes bye-bye. So we just get P. If B is 0, that whole correction term goes bye-bye. We just get V equals nRT. Oh, how do you like them apples? Right? That's the ideal gas equation. Hopefully you can appreciate the relation between the real gas equation and ideal gas equation. Account for gas particle volume, account for intermolecular forces of attraction, right? So really what happens, if you solve for pressure, pressure would be nRT over V, right? So if we do nRT over V minus NB, to get the pressure, you have to subtract that to the other side. So it's really a corrective factor that reduces the pressure, which is kind of nice. I will always give you that equation. And Scouts honor, I will not make you do a calculation with this on a quiz or exam because it takes forever, right? You got to multiply B by N first, limited by sig figs, N squared A over V squared, limited for sig figs, and then you have to do the subtraction, the addition, limited by largest absolute certainty or fewest number of decimal places, and then you got to do another division multiplication step depending if you're solving for T or N or V or P. Oh my goodness. It's highly unpleasant. But in one of our labs, if you take my class, we're actually going to do a lab where we go in lab and we solve for R. And we already know the value for R, so it's not like an unknown, it's a known unknown. And we're going to do it assuming ideal gas behavior, and we're going to do it again assuming real gas behavior. So we're going to use this equation and calculate which one gives us a more accurate value of R. Oh, and boy, the calculations are gnarly. We actually have a computer program put together where you have to put all your data in there that tracks your uncertainty and everything. And if you're off, it goes wrong, haha, redo the whole thing. You're like, no, there goes another hour of my precious life. And so you get a feel for, if you're at, roughly room temperature and 1 atmosphere pressure, roughly in laboratory conditions. Does it really matter which one you use, right? If we account for gas particle volume and intermolecular forces, do we roughly get the same value for R or not, allowing for experimental error? Or is it a pretty dramatic difference? So what I want to look at in the next board is what conditions, laboratory conditions, would be ideal conditions where we can make the assumption that A and B are 0 and just use this equation. Do you appreciate the PV equals nRT, the ideal gas equation now? So students moan about this. Oh, it's so hard. No, it's easy compared to what you should be using. I could make you use this one all the time, technically, right? So it's like, hey, thanks for the cheesecake, man. I love being able to use PV equals nRT rather than that monstrosity. Doable, but very tedious. So let's take a look at what ideal conditions are in a laboratory scenario. All right, so in lab, we're roughly atmospheric pressure, if you're at sea level, about 1 atmosphere, right? Or around 1 bar. And room temperature, depending where you live, anywhere from, I'd say 15 to 25 degrees Celsius range would be room temperature. Are those typical laboratory conditions? Can we consider and assume ideal gas behavior and not have a huge percent error in our calculations? Right? And what percent error is allowable? Is a 1% error okay? So we can use PV equals nRT versus the van der Waals equation, avoid all the nasty math. Is 5% error okay? Well, it depends, right? If you're a high-level research laboratory, maybe we're never using the ideal gas equation, right? We don't want any error in our calculations. But if it's an undergraduate laboratory, maybe 5% error or less is totally acceptable, right? I don't know. Depends on the individual, research lab, whatever you're doing. But what conditions would we say generally would be ideal? Well, let's take a look at the two factors, right? Remember that picture I showed you with the bigger container volume? The bigger the volume, the less relevant the gas particle size was. It didn't matter. They had more room to move. And as you shrunk the container volume, the gas particles took up a larger percentage of the overall space involved. So at lower volumes or higher pressure, the gas particle volume themselves becomes more of a relevant factor. It creates more error if you assume they're 0. So that means larger volumes or lower pressures are more ideal. There's more space, so the gas particle volume becomes less of a factor. So lower pressures are considered ideal conditions. Well, in a laboratory, what would we consider lower pressure? It's like saying, hey, you're tall. Okay. that doesn't mean much because what are you relating? Tall compared to Shaq may not be so tall. Tall compared to me, you might be pretty tall, right? Uh, or hey, you're rich. Well, what does that mean? Rich compared to me? Rich compared to Bill Gates. Big difference! Right? Or Jeff Bezos or something. So you always want to have a reference point so you can compare and go, oh, that's what I mean by prettier or stronger. You know, are you strong? Hey, you're strong. Compared to the mountain? No! Right? So we're going to make our reference point about 1 atmosphere or 1 bar pressure. So we're going to say, hey, you know, if you're at a typical laboratory around 1 atmosphere, 1 bar pressure, so about 760 millimeters mercury or torr, we can consider that ideal. And any pressure below that, we're good to go. If you start getting significantly higher than 1 atmosphere, the error in assuming gas particle volume is nil. It could start becoming a factor you need to be concerned about. Hey, yay for undergraduate laboratories. We can assume usually ideal gas behavior. Well, what about the interactive forces between them? Right? Think about the temperature. So if I got 2 particles, right, that are moving like this, and obviously in ideal gas, we're assuming there's no, it doesn't matter how fast they're moving, there's no interactive forces, attractive forces between them, what we call intermolecular forces. But if we allow intermolecular forces to come into play, right? If they're, when they get close enough, they got to be really close and they lock into place, they can impact each other, right? But it depends on their kinetic energy, right? If they're moving really fast, they may notice each other, but they're moving too fast for those intermolecular forces to lock into place or have an impact. So the higher the temperature, the faster they're moving, the less relevant the intermolecular forces are. They're like, hey, noticed you, bye-bye, right? But if they're moving slow, you make it colder. They're like, instead of moving like this, they're like, whoa, hey, look at you. And those intermolecular forces lock into place and things change, right? So the colder it is, the slower they're moving, the more impact the intermolecular forces are going to have, more relevant of a factor. Okay, so lower temperatures are bad. Well, not bad, but if you're assuming ideal gas behavior, lower temperatures would be bad. So ideal, whoops, I wrote the wrong thing there. So higher temperatures. I got my own answer wrong. Bloop, 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 bloop. I just saw that lower right there and rewrote it again. I put lower. So we want higher lower pressures and higher temperatures would be considered ideal. Sorry about that. Got excited. So higher temperatures are considered more ideal because bloop, the intermolecular forces are less likely to have any kind of impact. And again, what's our reference point? Roughly room temperature, right? Around 20 degrees Celsius or so. And anything higher than that, we're okay making that assumption of ideal gas behavior. So I'm debating on actually setting up a calculation and trying to go through it. It's probably a good idea too. It's going to take a while to set this up. So let's go ahead and do it, but be prepared for some tedious mathematics here when we actually use the van der Waals equation. All right, do your isokinetic exercises, do your jumping jacks, get that blood flowing, and we need some oxygen to the brain. Get some caffeine if you need it. Slap yourself like you do when you're driving down and you get tired at night. You're like, oh, wake up. Or you unroll the window and stick your finger in it and roll it up on your, and it wakes you up. You ever do that? Anyway, where are we going? Let's do an example here. Let's say we have a 1.89 liter balloon and we fill it with some N2O, a little nitrous there, a little laughing gas. And we put 1.52 moles of laughing gas in there at 13.6 degrees Celsius. It's a little colder than room temperature, right? What is the pressure? So what is the pressure of that? Now, obviously, we could do this assuming ideal gas behavior, P equals nRT. That's the easy way out, but no, we're not going to do that. The implication here, because I gave you A and B, I gave you the constant. Now, normally we'd have that, like if it was an exam, I'd probably, type up or photocopy a table from the handbook of chemistry and physics with, all these different gases and values of A's and B's. And you'd have to look them up. Or in lab, I'd make you look them up as well. But in this case, here you go. So A for N2O under these conditions, let's say, is 4.43 atmospheres times liters squared per mole squared. Sometimes you'll see it as bars there, liters squared per mole squared. And then B, that's the excluded volume per mole, right, is 0.0387 liters per mole. Let's calculate the pressure using the van der Waals equation or real gas equation. So give it a shot. You'll have to do it in multiple steps to track the uncertainty, but let's see if you get what I got. So obviously this is going to take this board, another board, and maybe a third board. I don't know. We'll see how squishy it gets, but and there's no way I'm going to do this live. Right, so I'm going to get as far as I can. We'll talk about it and move on till we're done. Oh, and then we'll go have a nice lunch afterwards. I couldn't even get any calculations done on my first board. I was just isolating my variable. So here's the van der Waals equation. So there's the P plus N squared A over V squared times V minus NB equals nRT. So I'm just solving for pressure. Let's isolate pressure. So that will be nRT. Let's divide through by V minus NB. So I get nRT over V minus NB. And then I'll move the N squared A over V squared over by subtracting that on both sides. So you can see how that's a pressure correction factor. Right, that accounts for the intermolecular forces. So the pressure is actually smaller than you would think if you account for real gas behavior. And then the NB accounts for the gas particle volume as well. So let's use this equation. And the first thing that we're going to do is, before we can do the subtraction here, we've got to figure out what NB is. See that? And then we got to figure out this term here. So we got to do the N squared A. Oh, it's going to be so unpleasant. So what I'm going to do is I'm going to calculate NB and then figure what that is and then plug it in, and we'll walk this through in a whole bunch of steps. Okay? So let's have at it. Not going to be pleasant. This is about as far as I could get on my first board, guys. This is just barely fit on here. Highly unpleasant. I think you'll appreciate by the time we're done why this will not be on an exam or a quiz, but definitely in lab, because you got time in lab. So here we go. So first thing I did is I took that 13.6 degrees Celsius and converted it to Kelvin, because we always have to do that for gas laws. So I added my 273.15, and I get 286.750 Kelvin, good to the 10th place from our uncertainty rules. Then I did the N times B, because I got the V minus NB. I want to figure out what that term is. So let's take NB, which is the volume of the gas particles. So moles is 1.52 moles. The excluded volume per mole, B, for this particular gas, N2O, under these conditions, 0.0387 liters per mole. So you can see how moles cancels out. And the three significant figures, I get 0.058824 liters. So I can now calculate the available volume for the particles to maneuver around. V minus NB, that's this term right here that I'm solving for. Boop. So the volume of the container, 1.89 liters, minus the volume of the particles, 0.058824 liters. Subtracting, so I'm good to 2 decimals there and 4 decimals, so I'm limited to the hundredths place. So I get 1.8311 liters. Good to 2 decimal places or 3 sig figs when I'm done. So normally with the ideal gas, if we use the ideal gas equation, we would use 1.89 liters. But using the real gas equation, we're using 1.8311 liters. Whoa! So here's the equation that we took the van der Waals equation and isolated pressure. Now we know V minus NB. So let's plug in our stuff. So N, 1.52 moles. R, 0.082057 liters atmospheres per mole Kelvin. Temperature, 286.750 Kelvin, good to the 10th place. Divided by V minus NB, which was 1.8311 liters. That's a big mess. And then we got to subtract from that the pressure correction for intermolecular forces, N squared A over V squared. So moles is 1.52 moles squared. You got to square the 1.52 and the unit moles, so it cancels the moles squared there. Ha ha ha, that's given in the value of B, or A, that's A. And then A is 4.43 atmospheres times liters squared per mole squared. Now sometimes you'll see that as bars times liters squared per mole squared, depending on if they're shooting for the International Union of Pure and Applied Chemistry, units of bar versus atmospheres that everybody else uses. So that's 4.43 atmospheres liters squared per mole squared. You can see how mole squared are canceled. Divide by volume squared, 1.89 liters squared. So hopefully you can see mole squared will cancel. Liters squared will cancel. leaving you with just atmospheres, which is good. Now let's look at the units here. Moles will cancel, Kelvin cancels, liters cancels, leaving you with atmospheres. So we're going to get atmospheres minus atmospheres. So a pressure minus a pressure correction factor. So let's do all, and we've reduced it to it's all multiplication division here, limited by fewest sig figs. All multiplication division here, limited by fewest sig figs. So calculate this term and calculate that term in the next step. And then we'll subtract them limited by the largest absolute uncertainty or fewest number of significant digits. So calculate those two terms for me and then subtract them and let's see what we get. Are you mentally exhausted yet? All right, I rewrote where we finished at the last board. All the units cancel out, leaving us atmospheres. So if you take 1.52 times 0.082057 times 286.750 divided by 1.8311, good to 3 significant digits, that's our fewest. I get 19.532 atmospheres, good to 3 sig figs. That's that first term. And then the pressure correction factor, the n squared a over v squared. 1.52 moles squared times 4.43 divided by 1.89 squared. Remember to square the number and the units. I get 2.8652 atmospheres, good to 3 sig figs. So that's the correction, assuming real gas behavior. So now we're subtracting. We're limited by largest absolute uncertainty or fewest decimals. That has 1 decimal place, that is 2. So we're limited to the tenths place, 1 decimal place. So pressure overall will be 16.666 atmospheres. Lots of sixes there. Good to 1 decimal, so that rounds up to 16.7 atmospheres. That's using van der Waals equation, assuming real gas behavior. If you redo the calculation using ideal gas behavior, PV equals nRT, a lot easier, I get 18.9 atmospheres. And so like I would have mentioned, if you assume real gas behavior, because those intermolecular forces are pulling those gases, reducing their impulse and how hard they hit, if you assume real gas behavior, you're usually going to get a pressure lower than if you use ideal gas behavior. We just mathematically proved it right there. And that's a pretty significant difference right there. But anyway, now you kind of see how to walk through the mathematics. It's not hard, it's just very tedious. The number one mistake I find people making is when you do the squared here, they forget to square the 1.52 or square the 1.89. By far, one of the biggest issues I find. All right, we got it. We are done with gases. Yeah!